Okay, I want so our screen it is appeared for everyone. It's right. So everyone can see our screen.
Yeah, we can
Yeah,
see our screen. Your
yeah. Okay, thank you. So okay, so at the beginning of start, which we are relying or which we are going to the describe or to investigate why the borehole imaging it is very important to we are starting from to studying the borehole image processing interpretation. It's from different aspects. So we have a raw image acquisition, then this raw image are going to a field or a stage of quality control to quantify or to judge on the acquisition steps of this borehole imaging. Then we are going to make some sort of processing for this imaging and apply an image enhancement technique and image enhancement technique to figure out a more reliable image. Then we are going to make a feature identification, then deep picking and analysis and geological interpretation. So why borehole imaging it is important? The borehole imaging is important because they support or it is can support a lot of answers for exploration and field development plan studies. For example, in the first main application, it is about for identify for structural interpretation. It is very essential or crucial for identify the subseismic faults, which they are act as some sort of barriers or non-sealing faults which can affect on studying a plan. Let's take an example about this. If we have an actually development field, this development field having many producing wells, so while in some intervals after recording and after production, we are running with pressure tool in some intervals or in some cases in when we are running an pressure tool in a field which having producing wells, we can see in some producing intervals of in producing layers that we have a version pressure. So this version pressure don't see or don't hear any depletion from the other wells. This may be to the structural barrier, such as subseismic faults or fracture or sealing fractures. So it is very important to study or to figure out what is subseismic structure analysis to see the if there are any barrier or any sealing element from inside or in the same reservoirs. So the another application we can detect the sedimentary analysis or we can which is sedimentary analysis and it is the most popular one from imaging. This feature or this application the image can be in this application the image can be calibrated with the core data and also you can acquire so you can acquire one or two cores in your field and calibrate your borehole, your borehole imaging with this course. So, so based on that, after the calibration, your images with the supplementary feature, which is they are getting from core, you have a calibrated image with core, and you can in the forthcoming wells you running with images in the most of the field, so it can provide you with the value current direction, which is which is the course cannot doesn't provide this. So this is another clarification or another explanation regarding the sedimentary feature analysis. We can classify the using images the sand it is which or identify what is the deformed beds or what is the inclined heterolytics, what is your cross beds, what is the high angle cross beds, and so on. And based on that you can identify the direction of your channel or the direction of your point bar and so on. The third one, it is a texture analysis. In the texture analysis, it can also, the image can provide you with grain size analysis for mostly of classic reservoirs, or it can also provide you with the grain size distribution, what is the fining up, what is the fine grain, and what is the coarse grain. So for petrophysical application, if we dealing with a carbonate reservoir, we can calculate by using borehole image logs. We can calculate a porosity from the image logs, which using calibrated images, which almost close to the porosity of vugs or fractures. So it can gives also a high resolution logs, which is capable for calculation of shale volume and sand volume, which will be useful in enhancing our net pay calculation. And there is a good study case for this, and we will discuss this later. The fifth application of our borehole imaging is regarding mechanical studies. It is by using the images we can determine the maximum horizontal stresses and the minimum horizontal stresses, and we can by using the induced fracture and breakout, and this is with these values or this structure elements will be very useful in the team of engineering in order to make a frag job or something like that. Okay, so here in this slide we are exploring the development of imaging tool from the beginning till now. So let's take an example from daily lifestyle, which is which is to stand from daily lifestyle to stand on the beginning of and the development of the borehole image tools. So in the first picture we can exploring a picture of cell phones, the development of cameras of cell phones. So at the beginning, we have a cell phone with a one camera. This is, and then by developing the and the companies which is they are responsible for manufacturing cell phones, they are developing their cameras such as increasing the megapixel and increasing the resolution, and then increasing the cameras in the mobile, not one single camera by two camera, three camera, and 4K, and so on. by the same idea and the same figure, we have an image, the borehole image tool. It is being development. For as the first generation of the tool, we are using the deep meter tool, which is a single three arm single electrodes. So this tool is a three arm deep meter tool, continuous micro resistivity measurement. So by the beginning, we started with three curve. Then by going to 1968, we add more arm to be more to be for sensor. So we are going to be four curves. And then we mount two electrodes in one single arm. So four arm, which and one thing by two electrodes per one arm. So we have eight sensors or of eight resistivity curves. Then we are going to development our tool until we are getting to until we are getting to the last stage or the last generation of the tool, which is FMI tool or XMI and so on, which is about 192 sensors per one tool. So at this stage, we cannot apply an image just by correlation between this resistivity curve. We can conclude or extract the Shiva or the dip attitude. So by continuing increasing the electrodes in the borehole imaging tool, we can here stacking these electrodes side by side to getting the borehole image tool. Okay, so from the beginning, what is the meaning of borehole image? The meaning of borehole image, it can be described, which is a map of your borehole. Okay, for a certain property, this map, it is distributed in 360 degree in your well. By the way, so this map, it is, I mentioned that for for a single property or a certain property, that such as we can have an image tool by using gamma ray, as Musa gamma ray, or can have imaging tool by resistivity curves. We can have imaging tool by using acoustics, and we can have imaging tool by using density. But in the market, the most popular one, which we have an imaging tool from it by the imaging tool which we can get from resistivity. This is the most popular one in the market. Okay, so again, the image tool can provide us a high resolution records of rock properties in 360. Then the image tool, it is looking in 360 degree, crossing our borehole. Then we can unroll or open this image to be applicable to be detected or applicable to be picking on some or some features. So we unroll this image, and from the north south direction, and the direction is going to from clockwise direction from north west south east. Okay. Okay, so we have here the borehole imaging families. We have two main families for borehole imaging. The main borehole imaging family, it is wireline logging image, while the second it is logging while drilling image. So we can extract an image, we can figure an image tool by using two main families, such as an image tool which while drilling, or imaging tool after finishing our drilling our well and then run with wireline. So for LWD imaging tool, the advantage for LWD tool, it is we have a 360-degree without any gaps. So i- in let we will have some sort of that we if get is an example for this, we can observe that this example we have a 360-degree image without any gaps between image, but this is which rely on this tool which getting from LWD. So as the tool it is rotate in 360, so there is no any gaps in this borehole image, while in the wireline image there is a gap between the arms, as we can see here. This is the arms we of image. These gaps, it will be included in here, it will be observed or clarified in here, which is the gap between bad and another, bad and another. But in LWD, it is one tool, it is one rotating tool. There is no gaps between between the arms or flaps or something like that. So we have a continuous image in 360. So this is which is an advantage or an key advantage for LWD tool. So the first Asmusal tool, which is the gamma ray tool, it can capture gamma ray, a 360 tool around the borehole. But the tool limitation of this, and it is not effective in carbonates, for examples, due to low variation on gamma ray response. So if you engulf or Gulf or Arabian Gulf and you run with LWD gamma ray as muscle, the most of the Gulf it is a massive carbonate, so there is no variation in this carbonate interval. So the image will not give you a big answer or big solution for this. So we go to the second class or second class in LWD group, which is the Asmusal density tool. This tool produce three types of images, which is the photoelectric image, density image, and standoff image. This application of image tool, which is getting from density, which getting from density, it is very applicable or very useful in the formation density variation, which is important to determine or to figure out the lithology differentiation and the structure analysis. So the most popular one, which is the AFR tool, this tool which is rely on Asmusal resistivity tool. In this tool, we can use the resistivity sensors with a high vertical resolution to obtain the image tool, and it is an excellent tool for detecting thin bed analysis, fractures, and fine sedimentological features. So the fourth tool in this family, it is the Bexstar or the ultrasonic group. This ultrasonic sensor, it is measure the acoustic impedance and travel time inside the formation. This is very capable for identifying fractures, faults, and bugs. The major application of this tool, it is very suitable for identifying the textural variation and the structural feature from or by using acoustic signals. So by going forward to our by going forward to the another tool, which is the or another category, which is the wireline borehole imaging. It will be, if we take an example from Halliburton, the tool in there, it is called with XRMI and OMRI. So what is the difference between XRMI and OMRI? The difference in them, it is in the first case, it is running with the tool which is running with in water-based mode, while the another tool, it is running with oil-based mud, uh, oil-based mud environment. Okay, so if we take an example for XRMI tool, which is run in water-based mud, in this tool, it is deployed after drilling, which offer a high resolution imaging in water-based mud. This XRMI tool, it's operating in water-based mud environment, which is excellent vertical resolution, which up to 0.16 inches. It's very or high sensitive to the wide range of resistivity. While the second tool, it is applicable for oil-based mud environment, and it is designed to running with oil-based mud, which offering 1 inch vertical resolution, which is less in comparison or precise than XRMI tool. So the market also introduced to us an advanced technology in case of oil-based mud tool or in case of oil-based mud environment. This is an oil-based mud environment. The market provide us with three different tools, which is the advanced tools, which is called Schlumberger QuantaGeo and Strat Examiner for Halliburton, and while Geo Explorer or MX for Baker Hughes, and we will figure out what is the difference or what is the applications between the OMR between the high or the advanced tools on oil-based mud and traditional one. So this is the Asmusel focused resistivity tool, which is the resistivity tool which is running under the category of LWD tool. In this tool, we having two transmitters and three sensor offsets. The first transmitter, it is with very to the first one is very near to the transmitter, which is can getting the high resolution or vertical resolution, while the midway, it is far from the transmitter, and from the transmitter to the sensor, and I can detect very high resolution from the far, and from the far sensor, we can identify the or acquire the resistivity data. So to make it briefly, from the near sensor, such as here, we can identify a high resolution or very vertical resolution, very high vertical resolution for your borehole imaging by using the near sensor from your transmitter, while the far sensor, it can we can detect the formation resistivity, which is such as true resistivity of your formation. So the sensor which rely on to detect the feature inside your formation of your resistivity in your formation will be rely on the near sensor, near one, while that the far one will rely on the RT or the true formation resistivity of your formation. Okay, so we have here, if we can observe in this, we have here this pins which is in the electrodes or which is in sensor. These pins are rotated in 360 degree or this sensor can rotate and can record 180 degree per one scan, this one scan per 1 foot. So this sensors or this pens, which is the sensor, uh, can acquire 180 degree or 180 value per 1 foot, which will in 360 degree. So can you see we or can you imagine that you have 180 degree data per 1 foot in 360 hole. So by this which by this tool or by this data, it is very sufficient tool or very sufficient data to acquire to make or to just being picking your features or picking your any sedimentary features or any structural element that you consider in your well. So the second issue inside the tool, we have here two transmitters. The first is transmitter with 2000 kilohertz, while the second transmitter which is 400 kilohertz. Why using this? Because it is they are relying on which is are responsible for the high resistivity or the high frequency transmitter. It is regarding or it is responsible for the phase resistivity which you are getting, while the low frequency mode or low frequency transmitter, it is responsible for your attenuation. So this tool also it is very useful in geosteering operations as the pens can acquire 180 degree reading per single or per 1 foot. So the second tool which is in the market or the second tool in LWD category, it is the ultrasonic tool. This tool it is can with looks like Pixstar. We have it have a range of detection of the tool. This tool it is have four transducers. Those transducers they are can covering in 360. The tool it is emit a high frequency sound waves, which is getting from which pulsing from a rotating transducer. This sound wave it hit the pore hole inside your the pore hole of your wall and then reflect back to the tool. So By analyzing the travel time and the amplitude of each echoes, the tool can create the 360 images of your of borehole surface. The ultrasonic image tool also it is based on the acoustics or based on the acoustic reflections the based on the acoustic reflections. First, we have piezoelectric transducers, which can emit and which can emit an which can emit ultrasonic pulses or short ultrasonic pulses, which is commonly it's ranging from 250 to 800 kilohertz into the surrounding mud. It is propagates These pulses, it is propagates inside your formation or inside your drilling mud and the head of borehole, and then this wave reflected and returned back to the your tool, and you can figure out this travel time and the amplitude of echoes in order to create your image. So our data for by using acoustics, we have two main properties. The first property it is that the echo travel time, which is delta t, can determine the distance between the borehole, can determine the distance to borehole, which is used it can be used in computing the borehole diameter and shape. The second property it is the echo amplitude, which is a reflect or an indication for the rock hardness, roughness, and fractures. And low echo amplitude can rely on or may suggest that we have some sort of fractures with or washout and bugs. Okay. So by going to our category for electrical resistivity tool, by in the category of wireline imaging tool, we are dealing with some sort of such as XRMI tool. In this tool, we have 6 pads. Each pad of this we have 25 electrodes, which is mounted by each arm. This tool is recording uplog and while and it and the tool is it should be it's mandatory to be in a good contact with or good coupling with the formation. So those pads should be recorded uplog and the pads are open and pressed inside the formation or to be in a good coupling with the formation with a certain pressure.
Ibrahim, ah,
Hello,
laisse-moi
any
sur le moi. Ça va.
So it should be in a good coupling with your formation, and the witness or the which is responsible for the job should check with the wireline field engineer about the pad pressure of this tool. This contact is very essential as this tool has very narrow depth of investigation, not such as not such as in deep resistivity or something like that. So this bad pressure will and also this bad pressure will depend on the whole shape and the whole robustity for some examples. So uh, at this tool, it is record 180 degree by 1 foot, which is mean uh, 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 we have 10 reading. We have 10 reading per 1 inch. So if we have this scale of inch scale, the images have in this 1 inch have 10 samples. So the XRMI comes with a high density data rate for quantifying or for observing or for making the imaging tool or display the image distribution of your borehole. This is the tool of XR of the Schlumberger, which is running in the water with mud. And we are going to speak about the theory or how the micro resistivity image tool can be functional or the physical functionality of this tool in case of water-based mud. The idea of this tool is that each tool having arms, these arms having many electrodes, those electrodes inject, and those electrodes can inject its current and then retrieving this injecting current will be retrieved back on the same pad. Okay, so by injecting the current and receiving it on the same pad, each sensor of it will be distributed or will be displayed and as one resistivity curve. So as we can see here by this pad, it is looks like we have 25 buttons or 25 electrodes. So by acquiring the data or acquiring the borehole while recording the imaging tool, we acquire by each bed 25 resistivity curve. So by observing by this, we have 25 resistivity curve multiply by a 6 arm such as in XRMI, such as in Halliburton tool, we have 150 resistivity curve per single foot. Okay, so it is very high mandatory or very high density data rate in order to make or in order to display an image in this case. Okay, so it's worth to mention also that the Schlumberger tool, they are not having 6 arms, they having 4 arms, but they make an additional, what is called additional extension for each arm. This additional thing or additional extension, it is called the flap. So they called this is bad and this is flap. So each arm of this having two section. The first section which is called the pad and second section which is called the flap. So we by multiplying pad and the flap by 4 arm, we have a four we have 8 displaying resistivity section. Okay, so this is the criteria for the imaging tool which getting from FMI, and this is the criteria for imaging tool which is coming from XRMI, and such as in Halliburton. So by going through the borehole imaging tool in case oil-based mud, in the theory in case of oil-based mud is different. such as we have here two electrodes, okay, which is A and B. We, in this case, make a current, induced current, which is being upper and lower electrodes, and we measuring the voltage or the potential between two pairs of this. Okay, so we inject the current which is coming from A and B, and we measuring the delta V, or the voltage or the potential difference between these two potential electrons. So we can observe that we have here 10 electrodes, 1, 2, 3, 4, 5, and then 10 electrodes, which is 5 pairs. So each pad or each arm will give me 5 resistivity pads. As you can see, by each arm here give us 5 resistivity pad, while in water-based mud, each arm can provide us with 25 resistivity curve. It looks like the coverage of image tool, it is 20. In case of oil-based mud, it is 20% or 25% from the coverage of water-based. So this is why the market introduced to us the, if you can remember, introduce another and advanced tools in case of oil-based mud, in order to overcome this coverage and coverage technique. So by going to this is an example of OMRI tool pad, which is oil-based mud imager, which is in Halliburton, for example. This pad, they have the OMRI tool. In this tool, we have 6 pads. Those 6 pads, they are separated with 3 feet spacing. Each pad of these having 12 electrodes, which is being 6 pairs, which, so we can getting 6 resistivity pads or resistivity curves per each pad. So multiply 6 resistivity curve by 6 arms, we having 36 resistivity curve in case of oil bismuth. Okay, so we have here a video which is we can here display on a video for this is a video which this displaying video, it is display how the OMRI tool, it is being recorded while we record our entire section. So after that, we can. This is the the first section of your borehole imaging tool. So the image tool, it is operating by using two primary systems. The, the first system, which is the first system, which is using measurement system, such as this measurement system, which is dealing with it measure the physical property of the formation, while the second system or second package, it is the orientation system. So the image tool have two segments. The first segment, it is regarding measurement system, while the second segment, it is regarding the orientation system. So this orientation system, it is tracks tool orientation in three-dimensional spaces, which they are very important for the image interpretation. So the image with without any orientation package, without orientation system, it is will be like your picture in your mobile. So the picture on your mobile which you are capture it, it is looks like you don't have any orientation of it. So, but if you have a compass in your mobile and align your orientation or align the directions while you taking the picture, so you have now an oriented image. So again, the first component, it is regarding the consist of sensors, which is directly measures the formation physical property, such as in tool resistivity tool, it can capture resistivity image, while the second component, it is relying on. So this is which we getting from the image, which we are getting from a measurement system. To make or to know its orientation, we should integrate it, what's called GBIT or navigation system or orientation package and so on. It should be linked to this with and ensuring that we have a correct alignment of the measurement. So in the measurement system or the orientation system or the orientation package, we have here three axes of accelerometer and three axes of magnetometer. Three axes of accelerometer, they are help in speed correction and determining the precise tool location inside your borehole, while three-axis magnetometer it is track it is measure the Earth's magnetic field to determine the tool orientation relative to the magnetic north. So the magnetometer system, it is responsible for calculation the tool declination, which is angular difference between the true north and the magnetic north. So to make it briefly, the orientation system or the measurement system, it is regarding the pads. The orientation package or the orientation system, it is will be regarding what you call gibbet. And this gibbet, we have three axis acceleration and three axis magnetometer. This acceleration determines the exact position of your tool inside your wall, while three axis magnetometer, which is looks like roughly speaking, it looks like your campus to determine where you relative to the determine your magnetic north and determine magnetic declination, and then determine your tool in order to relative to the true north. Mhm. So this is the basic quality check. Just by after acquisition our borehole imaging, we display we at the first of all we make a depth shift between the first and two run, the first run and second run, to being applied the all image data in a correct or they aligned on the same depth. Second track, it is the calipers, which is showing the difference between the calipers. Third track, it is calipers of term of the whole shape to figure out where is the washout and tight spot and so on. The first track, which is coming from the cable speed accelerometer, which is coming from three-axis acceleration, and this which is three curves of acceleration or accelerometer, and this curves of magnetometer, to make a basic quality check about your data that they are comes in a good response and good quality. And then we are displaying the measurement section, which is comes in pads or flaps. Okay, before processing, we displayed it as separate columns to figure out if there any faulty button or faulty section or mislocked section and so on. So after after basic quality check, your borehole image undergoes processing steps or processing procedures, and then to get the final products, which is a static image and a dynamic image. So the difference between them, that the static image that having a color palette along the borehole image from the top and the bottom, while the dynamic image, it is another color palette which will be introduced in your image, but for small or short interval, which maybe we may apply a color palette for your borehole image every 1 foot to get it in a dynamic range. Then, after finalizing it, we are going to after finalizing it, we are going to the high resistive, which conclude or which appear as a light color, while the low resistive, it's appear at dark color. Okay. So uh, in this case, it is one of the most important issue in case of oil-based mud. You should be taken in your consideration before or before your planning. You plan for running hole with imaging in case of oil-based mud. So when you running in, we are running in the borehole, we are running with the image in the case of oil-based mud environment, such as with the tool or with the traditional tool, such as oil-based mud in Schlumberger, such as OPMI or dual OPMI in Schlumberger, or OMRI in Halliburton, Earth Imager and Beaker. As you run with this technology, so you should be assured that your formation resistivity will be exceeding 20 ohm meter, because under this 20 ohm meters, these values will undergo less stable response between different apparent resistivity. Okay, and I will show you a case in this next next slide will be a case for this example. Okay, so by considering this issue, the market introduced to us um, a high technology tool with a tool with comes with a high frequency mode to get a better resolution in low frequency or in low resistivity reservoir. So if your reservoir, for example, ranging from 2 or 3 ohm meter to 20 ohm meter, so you are should going to the advanced technology, such as we mentioned before in the previous slides, to overcome this chaos or this unstable response of apparent resistivity curves. So let us figure out what we can see or will we detect if we run the traditional tool in the case of oil-based mud, in the case of resistivity less than 20 ohm meter. So this is our example. This is our gamma ray. This is our caliper and washout, the resistivity curve, and it is three modes of frequency. This is the first mode, which is low frequency, and the highest frequency mode. This is a line of 20 ohm meter. Okay, let's take this for example. So this interval or this part, for example, as we can see here, this is a low resistivity, and we can detect, or we in this interval we have record the three modes of high resist, low resistive, moderate, highest frequency mode. Sorry, mode of low frequency, medium frequency, a higher frequency. Okay, as we can observe here that in low frequency mode, it is the features, it will be very in colored way. There are some features we cannot delineate it precisely, but if we are dealing with the high frequency mode, the feature here, we have a more feature enhancement. The image is more enhanced, and we can delineate the feature very well than the low frequency mode. The third, the next zone, it is the zone above 20 ohm meter. So above 20 ohm meter, can you see this? And this is a low frequency mode. We have a low frequency mode. The data is being structureless, or the feature is less in this example, while the data comes with a high resolution, a high structure feature in a high frequency mode. So this is another example to get us the differentiation between low frequency mode and the high frequency mode. As we can see here, this is the same interval. It is being recorded with low frequency mode. We can see here there is no feature or there is no elimination on this in static image, while in high frequency mode there are the elimination. It is having more figure out or having more precisely being sharpened or being enhanced in and can be pegged correctly in this mode. So by going to the borehole imaging solution, the solution is the first of it. It is about structural analysis. So the first of all of our image, if we are going to the image at the beginning of the start, we are making the structural zonation by identifying the breaks such as faults and characterize our well into different segments based on structural depth attitude. So each grouping or each zone will have a structure depth or depth attitude different from another. So the main criteria also from structure analysis, it is to distinguish or to getting our structural breaks such as faults. For example, the which is by identifying there are main criteria or to identifying our faults, such as the difference between the dip attitude before and after your fault break, or fault juxtaposition, such as in this example, or occurrence of some sort of the deformation across the fault area, some in some cases the fault comes with associated with the fault echoes around the fault intersection. So this is an example for single well structural analysis. We can see here in the lower zone, we can see here on the lower zone of your bedding, it is closed up to, it is looks likely close to flat dipping with dipping direction. It was it looks like southwest direction, and the dip angle not exceed uh, 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 5 degrees. So by going up, we can will explore. By going up, we can explore here that there is a zone which is deformed zone, which is dip angle can reach up to 90 degree. Then above the zone, the dip, it is come being gentle again with 10 degree in the direction of the northeast. So by observing this criteria and noticing this criteria, we can here we there is a change comes in depth attitude and depth direction. So we can make a projection. We are go through a projection between the bedding plane along the southwest northeast direction. So we can observe that we have some sort of a fault, or we can detect there is some sort of a fault across this interval. So this is our bedding plane, which is comes in northeast direction, and this is the bedding plane which is comes with southwest direction. It is the fault intersection between it, and this bedding is comes is a gentle bed or gentle dip in southwest direction, and then there is two micro faults between this bedding. Okay, and as we can see, this the major fault Can you see this? This major fault, comes with this fault comes with some sort of jack juxtaposition and some deformation or some appreciation on this in its plane. And okay. So the second example for or second solution for borehole imaging is regarding the fracture characterization. By using the borehole imaging, it is it's very important to detecting your fractures and classifying your fractures. So by getting at the beginning the fracture definition, it is about some sort of discontinuity of plane as a result of that exceeding the tensile strength of your rock. If the stress it is more increased than the displacement of your rock, it will it will convert your fault it will convert your fracture into fault. So the primary objective for your of your of image, it was uh, to make a characterization for the fractures by using electrical images. Those fractures, and also we can by using borehole imaging int- integrated with another tool such as acoustic tools, we can classify our fractures, either it was open fractures or resistive fractures, for example. And then after that, after we are picking and classifying our fractures, either it was open or closed, we can count our fracture density and then apply some sort of processing and running module to detect the fracture aperture of inside the our formation, or inside the borehole. The second item, it is the present day stress analysis. It is by considering or by detecting the tensile failure, or by detecting the induced fracture and the breakout, we can detect the sigma minima and the sigma maxima. So by detecting the breakout, which is reflect on the minimum horizontal stress, and predicting the tensile or the induced fracture, which is rely on the maximum horizontal stress, which is very important info for engineering in order if they are dealing with the formation completion criteria, such as they are going to make a frac job simulation, or make drilling another wells. So they need the in situ geostress regime or orientation. So the third example, or the last one, it is the or the most popular one. It is regarding to give us a solution about fishes and lithophases and fishes and image attribute and the lithophage association and core image calibrated borehole image calibrated with cores. We can apply sedimentary analysis by picking our by picking our beds, or by picking our set boundaries, and then picking inside each boundary, between each boundary, the major criteria of your sedimentary feature or sedimentary features. So so by this we can delineate the trajectory of your channel, or the trajectory of your reservoir, by detecting or by picking your the cycles of your sedimentary beds. Okay, so that, such as here, for example, by the way, if this planar heterolytic example, it will be rely on some sort of point bar, and if you have some sort of a channel like looks like this, and your point bar, it is dipping across this channel, or in perpendicular way in this channel. So by picking this the direction of heterolytics, so the direction of this heterolytics, it is the perpendicular to the direction of this, it will be the direction of the channel. So by identifying where your point bar and or heterolytic facies is, you can, by this info, identify the direction of your channel, which is will be the perpendicular inside your heterolytics. Otherwise, if you have an example, this for example, this feature, for example, this feature, it is looks like it is scouring surface, and this is scouring surface, or uncomfort, or the base channel criteria. We can see here that the depth of this sand, it will be the same depth direction. So by picking your scouring and picking your sand lamination, you can predict that your channel, this your channel, it is the going toward toward some sort of this direction. Okay, so this is one of the solution of, while you picking your sedimentary feature of your borehole imaging. Okay, so to determine where is your scouring, where is your planar laminated, where is your heterolytics, and so on, to figure out where is the channel direction, where is the point by direction, and so on. This is, it should be side by side to be calibrated with the borehole, which should be calibrated with the core, because the core, it is comes with its ground truth, and propagate the image, this calibrated image in uncored interval. So finally, this is one of the geological application of borehole imaging tool. It is we here in this case, we picking our lithophases, and then we stacking these lithophases into faces association, and this faces association will be calibrated with the borehole, with the core image logs, with the core image, with the core images, and then make some sort of correlation between different wells and make some counting, and then finally we can observe that where is the channel system, where is the depositional system environment, and where is the value current inside our reservoirs. So it is some sort of integration of multi-disciplines to figure out the geometry regime of our reservoirs. So by the end of the day, I would like to thank you and thank Petro Diamentum to handle this session or this webinar, and thank all the audience which they are attend our this webinar, and thank you for your time. It's now for, time for question and answers. So, is there any question?